All right, guys. So we are going to talk a little bit about these position versus time graph problems. You guys ready? So you should have already done these, which is super helpful. Sorry, I was looking for like a different color pen. I remembered to bring one, but it's stuck to a folder. Crap. All right, so we're going to talk about these position versus time graph problems. Keep an eye on these. If there's something that you did differently, you can flag me down and see if I'm doing it wrong, or you can correct yours if I convince you that I'm doing it correctly. All right, so firstly, we're given an example where Robin is roller skating down a marked sidewalk, and they were observed at the following positions at the times that are listed below. This is a lot like when you guys did the buggy lab, right? This is just motion data. And so we've got position, which is represented by X, and time down on the Y-axis. So let's see, we should go ahead and graph this. We're going to go from 0 to 10 seconds. So can we go to 10 across here? 1, 2, 3, 4, 5, 6, 7, 8. I'm going to make these, I'm going to decide to make these so each one equals 2 seconds. I don't know if you guys did it the same way. The other way you could do it is extend it. And either one is fine. You'll get the same relationship. So we've got 10 seconds represented there. And my position is going to change by 30 meters. And I've got 1, 2, 3, 4, 5, 6, 7, 8 divisions. You could do this every 3. You could do it every 4. I don't know. How do you guys break it up? Any favorites? I'm going to do every 4. So the first one's going to be 0, 4, 8, 12, 16, 20, 24, 28, 32. So just squeak it in there. All right, so I've got at 0 seconds, I am at 10 meters, which is pretty good intercept up there. At 1 second, I'm at 12. At 2 seconds, I'm at 14. At 5 seconds, I'm at 20. 8 seconds, I'm at 26. Whoever collected this data was doing it a little bit erratically. So there we go. There's my dot. So I've plotted my position versus time graph for the skater. So there it is. How'd you guys do on that, okay?
Mine doesn't look like that at
Oh.
all.
What does it look like? Oh, dear. It goes down?
No, it goes like up and then it like goes over and then goes up again.
Okay, so one thing that I would check if that happened is make sure that you are matching up your times with your position, because if you did it one at each line without looking at what the values were, you might have done that. Do you want me to take a look at it?
I found it.
Okay.
I started at 0, 0 and not 0 to 10.
Gotcha. Yeah, that would do that too. And that's an easy mistake to make because it's got a 0 in it. So, if you're expecting it to be 0, 0, you might do that. Then it says, explain how you can use the graph to determine how far he was from the origin at 6 seconds. Now, remember, guys, this is a science class and not an English class. So if you can use a math explanation or you can draw a picture, I'm okay with that too. So if we need to explain how we use the graph to determine how far they were from the origin at 6 seconds, how am I going to do that? Here's how I'm going to do that. I'm going to draw an arrow. Here's where we are, right? If this is a line that describes the motion of our skater, here's where they are at 6 seconds. Right? I can just read that value right off the graph. So if I apply a best fit line to my data, I can just read that value. At 6 seconds, which is right on this line here, I can tell my skater should be at 22 meters. So my position in meters equals 22 meters. You guys practice writing math sentences in math class. Works in physics too. I had a teacher who used to say that math was the language of science, and it's pretty handy, to be honest, because sometimes it's a lot easier to describe something in terms of an equation or a math statement than it is to write it out in English. Next, write a mathematical expression that describes the skater's motion. This is saying write an equation. So this is a line, right? We've seen these before. It should be in the form of y equals mx plus b. So I know that my y-axis value here is actually position in meters. You can write out the word position if you want. If you want to take less time and space, it's perfectly okay to write that to represent position in meters. Equals our slope. So if we're going to calculate our slope, I would look at the first and last data point for a line. So my change in position is 20 meters. My change in time here is 10 seconds. So that's 2 meters per second. So I have 2 meters per second times my x-axis value, which is time, measured in seconds, plus our initial position, right? That intercept is our initial position, the position when time is equal to 0. And according to our data, when time is equal to 0, our position is 10 meters. All right, 10 meters. There we go. We could use this to solve this equation up here, right? If we want to know where we were at 6 seconds, 2 times 6 is 12, plus 10 is 22. It's the same as this value. It's pretty neat. So when you're doing problems in physics class, one of the things that's handy about learning all these different models is that you can use them to confirm that you got the right result, because they should always agree. If they don't agree, that means you might have a problem with something in your model. So if you said, okay, well, maybe you left the intercept off and you calculated at 6 seconds, you should be at 12. Well, those two things wouldn't agree, right? 12 wouldn't agree with 22. So then you have to decide if there's something wrong with your graph that led you to getting this wrong, or if there's something wrong with your equation. So those kinds of things are helpful. Was the speed constant over the time interval, and how do you know? Well, we can't tell from looking at the table, right? Because the table has time intervals that change. So that makes it tricky. We would have to think about if it makes sense for these gaps, because up at the beginning, we can see that the position is changing by 2 meters, but then all of a sudden we go from 2 seconds to 5 seconds, which is a 3-second gap. But down here is a 2-second gap, right? And so if we're moving 2 meters per second, a 2-second gap says we should change 4 meters then, right? Because it's twice as long as the time gap up here. And that ends up working out. So that we could look at the table and figure that out. The simplest way to be able to identify if something is moving at the same speed is to look at the slope. If we have a constant slope here, that tells us that our object or our person is moving at a constant speed. So down here is the speed constant, and we can say yes, because the slope of, and you can either say position versus time, or you can say position versus time. Either one's fine. The slope of that graph is constant. We also know that he doesn't change directions, right? It would be possible for the slope to be constant and the sign to change. So his speed would stay the same, but his direction would change. That's a possibility. That's a little advanced for this page. All right, so we've only got 2 or 3 minutes left in class. So I'm going to stop there today. You guys have any questions about this one? No? Is it starting to gel a little bit? Yeah, okay, cool. You guys did a great job on the quiz, by the way. You guys pleased with yourselves? You collected data and then used it to make a prediction, and it worked. It's so cool. Anyway. You have any questions, Zane? No? All right. I gave you a place in Google Classroom to submit your assignment, too. So I don't know if you saw that.